Okay, we're back and working on 1.2 limits with infinity, limits involving infinity. So I want to take a look at a polynomial and what happens with a polynomial as x gets really large. So if we consider f of x, which is equal to a fourth degree polynomial that you see in front of you, and I have the leading term squared up there, and then I compare it to g, and you've got the minus 2x cubed plus 3x squared, etc. And then I have g of x is equal to 3x to the fourth. Show that although f and g are quite different for numerically small values of x, they are virtually identical for the absolute value of x getting really large. So what I've done is I've put in a large value, and it's and pretty large. It's x is equal to 100. So if you're looking at the value of x equal to 100, you can see that it turns around a value of 298,029,506, whereas g of 100 turns around the value of 300,000. So if we look at the graph of these two polynomial functions, you can kind of see that, and you look at my scale, I've got a scale that is going from negative 10 to 10, and it's going from about negative 100 to 1,000. And the two graphs seem to just about converge, because what happens is that this leading term that I have squared off, it is the boss term, so it kind of rules the roost, so to speak. So what we're talking about is end behavior, and so for this one, the limit as x approaches infinity of 3x to the fourth, let me use functional notation with this. F of x is equal to the limit as x approaches infinity of g of x, and they're both going to converge to a positive infinity. Beep, I got to turn a beeping off. So, if I chose a few very small values around the origins, you see there's going to be a little difference here. But what we're talking about is x goes to infinity. Not only are they going to both go to infinity, they're going to behave very similarly after a very short while. And think about, x being 100, we're talking about going to 1,000, 100,000. Infinity's a lot bigger. So now in this next problem, I want you to take a look at the fact that I put a note there. The limit as x approaches infinity of 1 over x to the r is equal to 0. We want to consider end behavior. So with the end behavior of graphs here, I'm dealing with rational functions now. We can't take the limit because we'll have infinity over infinity with these particular graphs. It's really indeterminate. So we've got to do something now. I know this is new for some of you. I'm telling you, it's like bell ringing central here. So find the end behavior models. So I want to see what happens when x gets really large. But when I put in infinity here, it doesn't make any sense. We get this infinity over infinity. So we're going to do something called weird factoring. I want you to take a look at what I have down here. So what I'm doing in f of x, you see that I've got the 3x squared circled. So what we're going to do is we're going to factor out an x squared from the numerator and the denominator, and we're going to cancel it out, as you see. So now, what's tough about this, you're going to have to take a look at it yourself. When I factor out an x squared, I always do this from the denominator. What is the highest power of the denominator? And I factor that out. Weird factoring. Ready? So if I factor an x squared out of 2x to the fifth, I'm left with 2x cubed. X squared out of x to the fourth, I'm left with x squared. Minus 1 plus 1 over x squared. When I factor out an x squared, it essentially means that you are dividing each term by x squared. And the denominator, I get what you see there, 3 minus 5 over x plus 7 over x squared. So this is, again, it's weird factoring. We're going to factor out an x squared. So we've done that. We're canceling the x squared, and now we have the following. We're going to take the limit as x goes to infinity of 2x cubed. Now, if you pay attention to this, what's going to happen, you're going to have a positive infinity you're going to end up with. Let me get this a little bit thinner. So I'm going to, in the numerator, I'm going to have a 2, and then I'm going to have an infinity cubed plus infinity squared. Now that's still positive infinity, minus 1, well, like that's going to do any good or do much, plus 0. Because when I plug in infinity to 1 over x squared, that becomes 0. Okay, let me put this over. And then in the denominator, I get 3 minus 0 plus 0. When I plug in infinity in both those fractions, I just get 0. So you can kind of see that at this point, let me see how much room I have here, that I get an infinity for an answer here. I get infinity. So this diverges. So let me see. Make a little bit more room here. So for this one, it diverges and I get infinity. When we say diverges, it doesn't converge to a value. Okay, so there's that. And then for the second one, where we have equal, I'm going to plug in there. And I have to be careful because you don't always get what you would expect. So it's kind of strange. So let's see what we have here. We have 2 times negative infinity cubed plus negative infinity squared. And then you have the rest is just minus 1 plus 0 again. And then that's going to be over 3 minus 0 plus 0. All right. So for that second one, I'm going to put it down here. We end up getting 2 times negative infinity cubed, which is going to be a negative infinity. And then you're going to get plus an infinity, which is not 0. So, and in the bottom, you get that over 3 thing. Okay. Now, I'm going to leave this question up to you, what you think this is going to be. And I want you to look at a graph and see if you can determine what is this going to be. And then I'll come back to you. We have negative infinity plus infinity over 3. Do you think it's going to be 0? Or do you think it's going to be something else? So we'll leave that here. Just let you think on that. So that's kind of an intriguing thing, right? Infinity plus negative infinity plus positive infinity. Is that going to be 0? So I like you to think a little bit about this. And, don't worry too much. Just try to, don't worry, be happy kind of thing. All right, so now let's try it over here. The limit as we approach here. So we have our 2 answers here. So I'm just asking you to kind of hold off on that one. Then for the second one, so if you notice the first one, the degree of the numerator is bigger than the degree of the denominator, right? So our answers are infinity. So that's something that I had said with when you have when you don't have a horizontal asymptote, you have something else. So with this one, no horizontal asymptote, the degree of the numerator is larger than the degree of the denominator. So I'm going to challenge you to graph that and evaluate it and see what you have, and we'll talk about this in class. See what you get for a function. See if you can figure out what that one is. And we'll finish the next one. So when we plug in infinity here, we get this is equal to 2 minus 0 plus 0 minus 0 in the numerator. And in the denominator, we get 5 plus 0 plus 0 minus 0. So it turns out to be 2/5. So the limit for this one is 2/5. Okay, so the limit, I'm going to stick that right here, of g of x. Now, I'm doing infinity for this one, find an end behavior for both of these, and my time is kind of limited. So what I'd like you to do for both of these is graph them and see if it's making sense what the limits are in the numerator and what the limits are as x goes to negative infinity and positive infinity. So I'm saying the limit as x goes to positive infinity is 2/5. Maybe you want to take a second and do the limits as x goes to negative infinity. Okay, so they're going to be the same. So with this next one, let f of x equal x plus e to the negative x. Show that g of x is equal to x is a right end behavior model for f, while h of x equals e to the negative x is a left-hand model. So what I can do is I can say, well, what is the limit as x goes to infinity? Well, I'm going to rewrite this as the limit as x goes to infinity first of x plus 1 over e to the x. So when I plug in for that, I'm going to move my stuff here a little bit. And so I hope you can see this, that this is going to be whatever x is, that would be an infinity plus, now think about this, infinity plus 1 over infinity, e to the infinite power.
Mine.
Sure you can. So this is going to be infinity plus 0. So this term, 1 over e to the x, will go to 0. And this function, because when it gets really big, 1 over e to the x, that going to 0, you're really only considering the limit as x approaches infinity of x. So then with the next one, if you have the limit as x approaches negative infinity, double duty here, the limit as x approaches negative infinity. Oh, can you grab that? No. I'm opening a surprise egg. Oh my goodness, what's in this? Okay, sorry kids, little distraction. If the limit as x approaches negative infinity of x plus e to the negative x is you're gonna be putting in a negative value. So what's gonna happen is this is gonna be positive. It's gonna turn out to be a plus x. So you're headed in the negative range. So in this case, as you go to negative infinity, this term, the second term, is going to this second term is going to override the first term. Okay, so here's what the graph would look like. So the end behavior model, let me see if I can pull it all down here. Okay. Oh. It's like jumping all around there. Okay, here it is. So you can kind of see that what's going to happen is that, oh, and here I have the colored graphs. You can see that I have them up here. So the pink graph is x plus e to the negative x, and then the blue one is y is equal to e to the negative x, and y3 is x. So if you look at it, the second graph, y2, is really this, but you can't see it, okay? And the blue graph is e to the negative x. So if I can just highlight that, goes like that. Okay, that's all it is. And then the red graph is just y is equal to x, and you see that going here. So on the positive side, as x goes to infinity, you can see that everything is going to behave like, your function y2 is just going to behave like y equals x. Whereas x goes to negative infinity, you see that y2 is going to behave like the blue graph, y is equal to negative x, okay? So what's happening here, show that g of x is equal to x is the right end behavior model for f, while h of x is the left end behavior model for f. And that's because what happens is that as you're going either in the positive or negative direction, one of the terms is going to be relatively ineffectual to the whole expression. Okay, I'll let you play around with your graphing calculators to take a look at that. And if you'll notice at the very bottom, you can kind of see I have a point where you can see that y2 and y3 are pretty much the same function value, the red and the pink graph. So, even though like down here, y1, the e to the negative x is riding along the x-axis. But if you look at the negative values, it's following in pattern. The blue graph is really the pink graph. Okay, so we have one more, example 9, and we're going to, again, use the squeeze theorem for this. We're going to take the limit, we want to know as x. Okay, I'm going to take another pause here, kids. Oh, it's a surprise. The limit as x approaches infinity of sine of 1 over x. So what you're going to have to do here is you're going to have to figure out some way to bridge this. So you could take the limit as x approaches infinity and you're saying, well, how am I going to do this? It looks like, when you look at the graph of this thing, it looks like it's headed down to 0, right? Well, if we plug in here, we get sine of 1 over infinity. And the larger x gets, oh, we won't need to use the squeeze theorem for this. This, as x goes to infinity, we'll get to the sine of 0, which is, of course, 0. So as x approaches to infinity, this expression, with the limit, would go to 0. Okay, so I hope that was helpful for you. It's a cool Escher print. I'll put it together for you, Gabe. All right, so a cool Escher print with infinite dimensions. And I thought you would enjoy that. So since we're talking about the topic of infinity. So you guys have a great day today, and I will leave you some notes, and have a wonderful weekend. Talk to you later. Bye-bye.